This is how I beat GIMPS. First of all, what does GIMPS stand for? It stands for Great Internet Mersenne Prime Search. And it searches through prime numbers, and the biggest prime number to this day is... So I'm gonna make a prime number calculator in C++. And since I don't know how to do this the professional way, I'm gonna do it the noob way. After quite some time, I found a solution on how to check if a number is prime. So first we console in our number, and then we're gonna start dividing it by 2, then by 3, then by 4, then by 5, and so on until we reach that number. If it will get divided by one of these numbers evenly with no remainders, then we will know that it is not prime. But if all of these numbers get divided and there is a remainder, then we'll know it's prime. So after searching through the C++ dictionary, I found how to use a loop. After I coded a little bit, this is what I got. First, we're gonna enter our number and our check. After the user inputs our number, we are gonna initialize an I, and I is gonna equal 2 because we're gonna start dividing our number by 2. Then I needs to be smaller than number. So if number is 11, I is gonna grow because we have I++ all the way until it's all the way up until it's 10. And then right here in the loop, we're gonna have if number modulo I is 0. That means if the number divided by I has no remainder, so the remainder is 0, then we're gonna set the check as 1 and break the loop. This over here essentially just stops the loop. Then after we've done that, we're gonna check. If check is 0, in the start we're gonna set it to 0. If it's 0, the number is prime. But if it's not 0, like here, if the number modulo I is 0, then we're gonna set the check to 1. So we're gonna console out number is not prime. And now for the moment you've all been waiting for, I will press build and run. Enter a number. Let's try 14. 14 is not prime. And how about 11? 11 is prime. Let's try some more. 21. 21 is not prime. 23. 23 is prime. And finally, after using maximum brain power, I made a calculator that listed all the prime numbers up to 100,000. So practically what I did is I put this code in another loop. In that loop, we're gonna change number by 1. So we're gonna check 1. If that number is prime, we're gonna add it to the list. Then we're gonna check 2. If that number is prime, we're gonna add it to the list. 3, 4, 5, 6, 7, 8, 9, and so on. Now if I press play, as you can see, it is gonna list all the prime numbers up to 100,000. And it finished with 99991. And if I open a new Google window, I can search, is 99991 prime? And yes, indeed it is. But there's a catch. If we go all the way to the top, we won't see the ones smaller than 4,363 because Code Blocks, the program I'm using, has a limit on how long the console can be. But we will always see the last one, which is good. But this project is far from done. If I want to beat something as powerful as GIMPS, I need to have some very efficient code. So with that in mind, I found a solution. So instead of just dividing that number starting from 2 going all the way up to that number, what if we just stop when we reach half of that number. With this new algorithm, I was able to drop the time down from 180 seconds to 120 seconds while searching for the prime numbers up to 1 million. But how can I make this piece of code even more efficient so I can even stand a chance against GIMPS? The very next day, I realized that prime numbers can never be even. And I had realized this at first, but I never did something about this. So instead of searching through every single number, we're just gonna search through every single odd number. Using this method, I was able to drop the time even lower, all the way down to 114 seconds. As I was trying to make this piece of code even faster, I realized something kind of mind-blowing. According to a source, this number right here is the biggest prime number under 1 billion. We know that this is the biggest prime number ever found. And we know that this number right here is prime. And now take, for example, 2 to the power of 3. That would be 2 times 2 times 2, which is 8. 8 minus 1 is 7, which is prime. Let's try something else. 2 to the power of 5, which is 2 times 2 times 2 times 2 times 2. And that'll give us 32. 32 minus 1 is 31, and 31 is prime. Let's take one more example. 2 to the power of 4 is 2 times 2 times 2 times 2. And that is 16. 16 minus 1 is 15, and 15 is a prime, so now we know that 2 to the power of a prime number minus 1 is gonna give us an even bigger prime number. So shouldn't 2 to the power of 999,999,733 minus 1 be bigger than the world's current biggest prime number? Until I find out if this is a bigger prime number or just a mistake, and until I find a way to make this code even more efficient, that's all for this video. See you guys in the next one.